Let us start our lecture for today. In the previous lecture, we talked about metal semiconductor junctions. Then in metal semiconductor junctions, we mainly talked about two kinds of metal semiconductor junctions. The Schottky junctions, which can also be called rectifying junctions because they just behave like diodes. They allow current to flow in one direction. And secondly, we talked about non-rectifying junctions. Non-rectifying junctions can allow current to flow in both directions. So, in today's lecture, I'm going to demonstrate Schottky junctions and non-rectifying junctions for both N and P-type semiconductors. Our example is based on gallium nitride material, for which the band gap is 3.4 electron volts. Let us first consider the example of an N-type gallium nitride based Schottky diode. So assume we have a metal, and the metal is on the left side and the semiconductor is on the right side, and here is the energy band diagram of the two independently when they are not connected together. So in the previous lecture we talked about it in detail that for an N-type semiconductor, in order to form a Schottky junction, our metal work function needs to be greater than the semiconductor work function. So in our case, the example is gallium nitride, and for gallium nitride the electron affinity is approximately 4.1 electron volts, and generally this Fermi energy level is really close to the conduction band. So our work function would also be around 4.1, 4.2, 4.3 electron volts for N-type gallium nitride. Now, in order to form a Schottky junction on N-type gallium nitride, this metal work function should be greater than the semiconductor work function. So in this example, I assume a metal having a work function of approximately 5.5 electron volts. So let us consider that example in Silvaco TCAD. Let us run the environment of Silvaco TCAD. Here is the environment of Silvaco TCAD, and I have already written a code for this. So let me open the code. This computer is a little bit slow, so kindly stay with me. Here is the Silvaco TCAD code for the gallium nitride based Schottky junction. We defined a work area. I don't really want to go into the details of the code because we discussed the code part in detail for the PN junction diode lecture. So I will just run through the simulation. So we have defined a work area from 0 to 350 in x direction. As I already told you in the previous lecture, that in this code I'm using a scaling factor of 100 in x direction, and in y direction the scaling factor is 1. So in x dimension our structure would run from 0 to 350, and in y direction our structure runs from -0.1 to 10. So let me run the simulation so that I can show you the structure. Here is our structure. As I already told you that in x direction it runs from 0 to 350. and in y direction it runs from minus 0.1 to 10. Then we define region number 1, which is gallium nitride, and here are the coordinates for region number 1. So going to the figure, this region is our region number 1, and based on the coordinates it goes like this, as you can see. So this is our region number 1. Let the code finish the running so that I don't have to scroll up time and time again. And the impurities in region number 1 are donors with electron concentration of 1 into 10 to the power of 17 per centimeter cube. Region number 2 is anode. The material is titanium. So this is our region number 2, titanium based. Region number 3 is anode. The material is tin. Here is our region number 3. The material is tin. Let me zoom it out once again. And region number 4 is sapphire. As I already told you in the previous lecture that gallium nitride is generally grown on some sort of substrate, and in this example our substrate is sapphire. Then after defining the regions, we actually define meshing for our structure, and here is the code for meshing. In the structure you can display meshing by right clicking on the structure, then left click on display and click on this icon. So now you can see the meshing. And generally for devices we define denser meshing for crucial regions and less dense meshing for regions which are of less interest to us. So in this structure I would like to define this contact as Schottky contact, and that's why I will define denser meshing over here. Let me remove the meshing from it now. So as you can see we have got two contacts, but I'm mostly interested in just showing you the proof of concept, so I've only defined this contact as a Schottky contact. And I've defined the work function of this contact later in the code. Here I've defined some properties for the gallium nitride material, and above that I've defined a work function for the anode contact. This contact at the top I've defined it as anode, and I've allocated a work function of 5.5 to the anode contact. And then later we have some commands for plotting. Excuse me. And after that I've code for running the simulation from 0 to 4.5 volts. So as I told you that in order to achieve a Schottky diode on n-type material, our metal work function should be greater than the semiconductor work function. And inside the code I've assumed an n-type semiconductor material with electron concentration of 1 into 10 to the power of 17 per centimeter cube. And generally our Fermi level is really close to the conduction energy level, and electron affinity for gallium nitride is 4.1 electron volts. So our work function for the semiconductor would also be around 4.1, 4.2, 4.3 electron volts. I've assumed a work function of 5.5 for the metal in order to fulfill this requirement that our metal work function should be greater than semiconductor work function, as you can see inside the code. Here I've defined a work function of 5.5 electron volts for the anode. So this kind of structure is going to give us Schottky behavior, and here is the energy band diagram of the same structure under thermal equilibrium. But under forward bias, this Schottky barrier would be slightly reduced. Let us focus on the energy band diagram of the Schottky diode under thermal equilibrium. So basically for this structure, as we can see that we got a Schottky barrier, phi b naught represents the Schottky barrier, and we got a built-in potential. It's a Schottky diode, or it shows rectifying behavior, because as you can see, when we apply positive voltage to it under forward bias, we see that the barrier for electrons to move from the semiconductor to the metal is reduced. So electrons under forward bias can easily flow from the semiconductor to the metal, but we still got a barrier for electrons to move from the semiconductor to the metal. So basically we have the flow of current just in one direction. That's why it shows Schottky behavior or rectifying behavior. Now let us run our code now. In fact, the code is already run, but I want to show you a few things inside this structure. So in the structure, I want to show you the energy band diagrams. So I define a cut line over here on the Schottky contact, and then I want to show you the conduction energy level, the valence energy level, the electron quasi-Fermi level, and the whole quasi-Fermi level under thermal equilibrium. So as you can see over here, we now got a barrier for electrons, and this is under thermal equilibrium. But under forward bias, we also got a simulation under forward bias, and we got three figures at 3.5 volts, 4 volts, and 4.5 volts. Let me show you the energy band diagram of this structure under at 4.5 volts. Display. Instead of that, I'm interested in the conduction energy level, electron quasi-Fermi level, valence energy level, and whole quasi-Fermi level. So now we can see since this is just an n-type semiconductor, so we only want to look at the electron quasi-Fermi level. So now we see that under forward bias, this barrier for electrons to flow from the semiconductor side to the metal side has actually reduced. Now compare it with the energy band diagram under thermal equilibrium. We got a big barrier under thermal equilibrium, but under the application of forward bias, this barrier is reduced so that current can easily flow from the semiconductor to the metal side. And in this case, we actually applied positive voltage to the metal side and negative voltage to the semiconductor side. And you can also see the Schottky behavior from the current voltage characteristics of this device under forward bias. So as you can see, this device has a turn-on voltage of approximately 0.7, 0.8 volts, and then the current starts increasing. It goes up to 200 milliamps at 4.5 volts. So now that we have looked at the Schottky junction, our rectifying barrier, I would also like to show you a non-rectifying barrier for metal deposited on an N-type semiconductor. For rectifying barrier, the condition is that the metal work function should be greater than the semiconductor work function for an N-type semiconductor. For a non-rectifying barrier, the metal work function should be less than the semiconductor work function. Here the semiconductor work function is around 4.2, 4.3 electron volts. So I'm going to assume a metal work function of around 3.5 electron volts in order to achieve a non-rectifying barrier. So let's go back to the code, and inside the code I'm just going to make one change. Excuse me. I'm changing the work function to 3 electron volts, and let us run the simulation once again. Let us look at the energy band diagram of this structure under thermal equilibrium. So for that purpose, I go to Tools, Cut Line, I'll draw a cut line over here, and then we look at the conduction energy level and the valence energy level, and also at the quasi-Fermi energy levels. As we can see that since this is an N-type semiconductor, so as this is metal deposited on N-type semiconductor, so we are mostly interested in looking at the conduction energy level behavior. And now we can see here is our Fermi energy level, which is constant throughout the structure under thermal equilibrium. Now you can see that we got a really small barrier over here for electrons to flow from the semiconductor, from the metal to semiconductor. But we got no barrier for electrons to flow from the semiconductor side to the metal side. So in this case, we call it a non-rectifying barrier because carriers can flow in both directions, and this is also obvious from the current voltage characteristics of this structure under forward bias, where you see that we see a linear relationship between the anode current and the anode voltage as compared to the Schottky diode, in which we have a turn-on voltage. So in this case, we see a linear behavior of the current versus voltage, and that also signifies its non-rectifying behavior. So far we talked about metal deposited on N-type semiconductor. Now let us talk about metal deposited on a P-type semiconductor. So assume, for example, here on the left we have energy band diagram of metal, on the right we have energy band diagram of a p-type semiconductor. This is a p-type semiconductor because the Fermi energy level is close to the valence band. And for a p-type semiconductor, for a non-rectifying barrier, the condition is the metal work function should be greater than the semiconductor work function. But for a Schottky junction, or we can also say for a rectifying barrier, this metal work function should be less than the semiconductor work function. Let us figure out the semiconductor work function first. So we know that for a p-type semiconductor, the Fermi energy level would be close to the valence band, and chi for gallium nitride is 4.1 electron volts. Now 4.1 plus approximately 3.4, that makes it 7.5. So our semiconductor work function would be close to 7.5 electron volts. So we need a metal which has a work function less than the semiconductor work function in order to achieve a rectifying barrier. This is an example of a non-rectifying, but first I want to show you a rectifying barrier. So for a rectifying barrier, phi m, or the metal work function, should be less than the semiconductor work function. So let us assume a metal which has a work function of 6. Generally, we don't really have metals where the work function is so high, but platinum has a work function which is close to 6 electron volts. So I'm going to assume a work function of 6 electron volts for metal, which is less than the semiconductor work function for p-type gallium nitride, because the Fermi energy level would be close to the valence band and the semiconductor work function would be around 7.5 electron volts. So let us make the corresponding changes inside our code. Now in this case, instead of donors, we want to introduce acceptors. And also the semiconductor work function should be less than the metal. The metal work function should be less than the semiconductor work function for this example. So let us make sure, but I'm going to make it around 6 electron volts. Let's not make it too less, because then the barrier would become too high. So assume a metal work function of 6. The semiconductor work function for p-type gallium nitride would be close to 7.5 electron volts. Here the metal work function is less than the semiconductor work function, so it should give us a Schottky barrier, or a rectifying barrier. Also now since we have a p-type semiconductor, so we need to apply the positive voltage to the semiconductor and the negative voltage to the metal. So I'm going to apply the positive voltage to the cathode end now. And I'm going to run the simulation. Here is our structure under thermal equilibrium, and I want to look at the energy band diagram of this structure under thermal equilibrium. And since this is metal deposited on p-type semiconductor, so we are more interested in looking at the behavior of holes. So as you can see, there is this built-in potential for holes to move from the p-type semiconductor to the metal. Similarly, we have this Schottky barrier for carriers to flow from the semiconductor to the metal. And we can see the Schottky behavior or the diode behavior from the IV characteristics of this structure as well under the application of forward bias voltage. The turn-on voltage in this case is approximately 1.2. It depends on the work function. If you bring the work function of the metal close to the semiconductor work function, then this turn-on voltage would be reduced. And if you take it far away from the semiconductor work function, then this built-in potential would increase, or this turn-on voltage would increase. But the point is that we see the Schottky behavior in this case when the metal work function is less than the semiconductor work function for a p-type semiconductor. And here is the energy band diagram of the same structure under the application of forward bias voltage. So now you see that under forward bias, this barrier for holes to move from the semiconductor to the metal has decreased, resulting in increase of carrier flow under the application of forward bias voltage. Compare it to thermal equilibrium, where we got a big barrier, and under forward bias, this barrier has reduced. And finally, I want to show you ideal non-rectifying barrier for metal deposited on a p-type semiconductor junction. And for this case, the condition is that our metal work function should be greater than the semiconductor work function. Our semiconductor work function for p-type gallium nitride, as I already told you, would be around 7.5 electron volts. And in order to achieve a non-rectifying barrier, we need a metal whose work function should be greater than the semiconductor work function. Generally, we don't have semiconductors whose work functions are greater than 6 electron volts, but for the purpose of simulation, I'm going to show you that. So let us now change the work function of this semiconductor to approximately 8 electron volts, which would be greater than the semiconductor work function. And I've run the simulation now. Here is the structure under thermal equilibrium. And since this is a p-type semiconductor, we are interested in the behavior of holes across this junction. And as you can see, this is the constant Fermi energy level under thermal equilibrium. And we can see that there is a really small barrier for carriers to flow from the semiconductor to the metal side. However, there is no barrier nor for holes to move from the semiconductor to the metal side. So this structure will show a non-rectifying behavior. And we will see that in the IV characteristics of this device as well. So here is the current voltage characteristics of this structure, and as you see now the current is linearly proportional to the voltage, signifying non-rectifying behavior of this structure now. And as I already told you that generally we don't have metals whose work functions are as high as 8 electron volts. So a good way to apply good contacts to p-type gallium nitride is to dope the p-type gallium nitride material heavily and then apply metal contacts to it, resulting in tunneling behavior, and that would give you a good current flowing across the metal semiconductor junction. That concludes the simulation for today, and I will see you next time, inshallah.